we just spoke of how the equations of motion look in two-dimensional motion with constant velocity. Now we're moving on to two-dimensional motion with constant acceleration in a plane. That is basically in a plane represents two-dimensional motion. So in case of constant acceleration, the acceleration vector remains constant in both terms of magnitude and direction. The key equations that we'll look into is your velocity and your position vector. So in one dimension, we saw that v is equal to u plus at, or as a function of time. If I want to represent it as a function of time, I can write v of t is equal to u plus at, right? When it comes to two dimension, the same v of t has to be represented with vector notation u plus at. This shows that they are in vector form. That is, you have I, j, and k components with all of them. See the difference? Here there's no arrow, there is an arrow over here. So this indicates that, so basically the arrow indicates this, I, j, k components. Okay, it's not exactly a ideal representation, but you guys got the funda. So this is to do with your vector. When it comes to your position, you have your x of t or y of t. So I'll write x of t first. X naught plus ut plus half at square, while your y of t will be y naught plus ut plus half at square. This is for your correct one-dimensional motion. So when we are dealing with one-dimensional motion, our equations looks like this, the position vector. So if I rearrange in all of that, you'll get your displacement vector. But when it comes to two-dimension, so our representation changes a bit. Instead of x and y, we represent using r. So r of t is equal to r naught in vector form plus u in vector form, or we can write it as v naught, left to you guys, plus a in vector form t square by 2. So basically, two-dimension will be a combination of this two. Or you can go with, if it's three-dimension, then it will be combination of x, y, and z. That's it. So this is in general, right? All of this is in general. Now in component form, let me show that. In component form, things will get a bit complicated. Not too much. So position vector in component form. Okay, so it would be just something like this. R as a function of t is equal to x of t plus I cap plus y of t plus j cap. That's it. So please understand which part are your vectors and which part are your magnitude. So these things represent your magnitude, while your I cap and j cap represent your direction. Okay, and here x of t is your same thing as 1 being this, or let me write it off. So x naught plus v naught x t plus ax t square by 2. So this represents the initial, not represents the initial part, and x represents along x-axis. Okay. So there's a bit of representation that is we need to adopt over here. If not, everything is the same. This is y naught plus velocity along the y-axis plus acceleration along the y-axis t square by 2. So there is no arrow over here. You need to see that there are no arrows over here. Because arrows as in vectors. Why is that? Because these are one-dimensional components or one-dimensional. These deal with one dimension. Okay, so all this is okay, but I just want to give you guys one more aspect. It might look a bit complicated, but yeah, I need to do this though. I don't have space over here. I'll do it here. So if I consider your x and y axis, let me do it here. I don't have space. Yeah, now it's better. So this is to do with your position vector graphical view. Need this much of space. Let me start off with the most simplest thing. Say a particle moved from point A to point B. That's your Ri. That's your Rf. Now, I can talk about Ri and Rf in this manner. First is I can talk about the initial part. So I can draw and set a bunch of lines. This is the projection of the particle onto your x and y axis. Okay. So this is onto your x and y axis. Oh, I needed more space actually. This would be an example of retardation. I'll just have to reduce this a bit. That's it. Nothing else. Or I. Guys, it's not complicated. I'm just taking time to draw and stuff. So that's your projection onto x and y axis. Projection onto x and y axis. Now, this is nothing but your initial displacement, right? This is your xi or x naught and y naught. Agree? So this points your x naught, y naught. If the same velocity would have been maintained, right? Say for a second or so, the object would have traveled, say, till this point, So this length, again, I'm going component by component. This would have been representing x, v of x into t. While this component, the remaining component is because of what? Why is that we have this extra bit of displacement? It's because of your acceleration along the x-axis. Again, guys, the total displacement along the x-axis is x naught, v naught x. This is v naught x into t. So if the object had continued with the same velocity, it would have reached over here, right? You can see that. Within a second, it would have reached over here. But why is there an extra bit of displacement? Because it got accelerated. And from here till here, let me work on this again. From here till here, this represents total displacement, XF. Agree? So you can see that it's a combination of the particles movement along the x-axis is a combination of the initial displacement, the velocity, the displacement because of the initial velocity, whatever velocity it already had, and the other bit is because of the acceleration of the particle. And this will give us the total displacement. Similarly, if a particle happened to travel for the same, say 1 second itself, it would have reached over here technically. Right? So this part is nothing but your V naught Y T, okay, from here to here. But what is this extra bit? I mean, where did this come from? This is because of the acceleration it got along the y-axis. This is your half AY T square. And all in all, this entire length is what is your total displacement, that is YF. And RF is a combination of XF plus YF. And if I happen to join all of this, there's a few more things. It might look a bit complicated. All I'm doing is joining lines. This part, let me keep it light itself. This part, no, I can't do that. This part, this vector gives your, VT. And finally, we have this part is because of AT square by 2. Okay, so RI, VT and AT square by 2. Okay, V initial, T and half AT square. So VF is a combination of RI plus VIT plus half AT square, and that's our, this formula. So I'm representing it as V naught, sorry. So this will be our V naught and this is R naught. R naught, V naught T, and yeah, that's it. Okay, so it is a bit complicated, the diagram that is, but if you understand it part by part, it's quite simple. So again, watch and draw it the same way as I have. All of this exercise will add up. It might look like what is the point of this, but all of this will add up. Okay. And what else we have? We have velocity in component form. So we'll just end with that. So velocity in component form. Okay, let me actually remove this. Let me keep it to this. So V of t is a combination of V of x as a function of time, I cap. So this will give us the magnitude and this will give us the direction, plus V of y as a function of time, j cap. So V of x as a function of time will be equal to V naught x, right, into acceleration along the x-axis into time. I can write where, and V of y as a function of time is V naught of y plus ay into t. As simple as that. And yeah, this too also we can represent with a graph. I'll not take a lot of time. This is quite simple actually. Not a lot of variable. So this also deals with your vectors. This is initial, say this is final. This is V0 and this is Vf. So this is a combination of, if I again do the projection and stuff. So if this is projected, this is projected, the velocity is changing clearly. Why is it changing? Well, along the x component is changing because of V naught x is how I represent. The extra bit is because of this extra bit is because of correct acceleration along the x-axis. And here this is your V naught y. And this extra velocity it's getting because of acceleration along the y-axis. And anything else? Yeah, this would represent your acceleration component in general, right? AT. So this is also one way of representing your vector. V of t is equal to V naught plus A t. This is another representation. This is 1 and this is 2. Okay, again, there are many representation depending on case by case. We'll have to look at them. So we started off with accelerated motion over here with a constant acceleration, that is. So in general, we can write these equations, or not that, these equations, right? And then we started looking into component form. They started looking a bit complicated. But if you go part by part, it's very simple. So this also can be represented with vector form, right? Vector diagram and all of that. So that was your position vector. Your velocity vector looks something like this. And that's it, right? Okay. Copy everything, don't miss anything. So that can be your heading. And I missed arrows over here. So you basically copy this, okay? Don't copy that. Copy this. Then the next heading is your component form. I need to copy this. And this. The velocity in component form. That's the heading. And we deal with this.